I am Jim Peebles from the university. I will be I will serve as chair for the first two talks and then meta-chair for the next two. I first met John in 1968 when I came to visit Caltech. The meeting stuck in my mind. He said, first, glad to see you here. Then he gave me a short tutorial on quasar absorption line systems. He told me about an open issue. Do these systems arise from material blown out of the quasar, or are they intergalactic? He said, we have to invent a test to distinguish between these two, and let's get to work. The paper appeared shortly afterward. Here was a committed scientist. Buell, you worked with John on quasar absorption line systems a few years later. Well, you remember here. The subject was in a lot better shape then. You will now tell us the present state of this subject. Buell Jannuzi.
Thank you. Good morning. I've been asked to review John's work regarding quasar absorption lines. I will do this in a selective and biased manner, focusing on a few of his many contributions that are examples not only of his outstanding scientific abilities, but also of the great leadership he provided to his colleagues, postdocs, students, and the astrophysics community. Whether John was showing us how we should analyze a quasar spectrum, advocating for a major new experimental or observing facility, or leading a decadal survey of astronomy and astrophysics, he was always a superb leader. He was always thoroughly prepared. He worked with tremendous force and focus and productivity, and force. For those of us who were fortunate enough to work with him, he inspired us to always do our very best. John also liked to have fun, and while he found joy in many things, particularly his family, he found astronomy and astrophysics fun, and he helped those of us that he mentored find the fun in our work as well, whether we were contemplating a major question about the nature of the universe or trying to compile a new Fortran program. John loved being a scientist, and he also loved sharing his passion for the work, both the process and the results, with the rest of us. Well, John was interested and studied quasars and quasar absorption line systems for 40 years. Most of his published work came in two very productive periods, the 1960s and the 90s. These two apparent bursts of productivity were the result, in part, of John's reaction to the availability of new data. In the first case, it was the discovery of very distant quasars and the ability to obtain spectra of their rest frame UV light with ground-based telescopes. In the second, the ability of the Space Telescope to study the same UV light, but now as it interacts with the material in the nearby universe. I was alive during both of these periods, but of much more use as a potential collaborator in the second part. Now, it might seem that there was a gap here, but John was actually making major contributions to quasar absorption lines during that period as well, and we'll talk about that. In a 2002 interview, John said that he started looking at problems to work on in addition to the solar neutrino problem at the urging of Professor Fowler at Caltech, and that it was luck that took John to the study of quasar absorption lines and quasars. Well, maybe. John certainly believed that science often proceeds along unpredictable paths, but John also had a great ability to consider the broad implications and context of new data or experiments, and then to identify which analysis technique or physical calculation might most productively lead to new insights when applied to the available data. So John's successful work on problems other than the solar neutrino problem were not a matter of luck. Perhaps luck determined which important problems John found fun, but it was not luck that enabled John to make substantive and important contributions to our scientific knowledge over and over again. One of the events that led John to his first burst of activity on quasar absorption line research was a spectrum obtained by Martin Schmidt of the quasar 3C9. While quasars had been discovered in 1963, 3C9 has a redshift large enough that the rest frame UV radiation shortward of the wavelength of Lyman alpha absorption from atomic hydrogen would reach our ground-based telescopes. The radiation has to be redshifted enough to avoid being absorbed by the Earth's atmosphere. Gunn and Peterson quickly pointed out that continuously distributed neutral gas between us and a distant source should absorb the rest frame UV light from the source, causing a continuous depression of the flux, just how much depending on the amount of material present. This proposed continuous absorption would become known as the Gunn-Peterson effect. The spectrum shown is not Schmidt's, but one subsequently obtained by Bev Oak. As Oak pointed out in his paper, his observations, and for many years of many other quasars until we got up to much higher redshifts, could at best be used to place a limit on the amount of this continuously distributed hydrogen. Contemporaneously with Gunn and Peterson, Bahcall and Salpeter considered in more detail whether and how we might derive the physical properties of any gas between us and the distant quasars, particularly gas that might be condensed into discrete clouds associated with intervening luminous material. For example, gas associated with clusters of galaxies. In their 1965 paper on the interaction of radiation from distant sources with the intervening medium, Bahcall and Salpeter said, quote, "We suggest using the intense continuum emission from quasi-stellar sources to probe the intervening medium at a variety of distances." This proposed absorption by discrete intervening systems is called by some of us the Bahcall-Salpeter effect. The increasingly sophisticated simulations of the universe that have been produced since 1990 have shown us, and I'll try and touch again on this later, that the detailed appearance of the intergalactic medium can be complicated, depending on secondary astrophysical processes which are only just getting included into the models. But back in 1965, while there were still many details to work out, a basic picture of what we might see along the sight lines towards quasars was beginning to be imagined by Bahcall and his colleagues. Over the next few years, John started to work out how we could learn about the physical properties of the gaseous material that might be between the distant quasars and us, and he was eager to help analyze the rapidly growing data set of new spectra. John recognized that his ideas and the methods he wanted to use needed to be tested against the best possible data, and he valued his collaborations with the expert observers he was able to work with at the time, Greenstein, Oak, Sargent, Schmidt, and many others. But while he always respected the integrity of the data, he also required that the analysis of the data be handled in a self-consistent and logical manner. So when strong disagreements developed in the community about the reality of various identified absorption line systems, or whether or not such systems were intervening or physically associated with the quasars, John was able to lead the community to improved understanding by presenting both physical arguments and improved methods of analyzing the quasar spectra. One of the reasons there were controversies and disagreements about the absorption line identifications was that while the spectra being obtained were impressive given the available technology, they were not initially of high signal-to-noise ratio or high spectral resolution. This is an example. So it was hard for most researchers to reach strong conclusions. This was particularly true when it came to the task of trying to isolate related absorption lines, groups of discrete features that were all being caused by gas in a single object or volume of space, sharing a common redshift. If you have several such systems along a single line of sight, the task of unambiguously identifying the lines can get quite complex. John systematized this process using his knowledge of atomic physics and his ever-growing knowledge in computing to write code that allowed him to reproducibly and objectively produce lines of candidate systems in a given spectrum. This code allowed him to perform the same task for simulated or dummy spectra. He used Monte Carlo simulations to test the robustness of his identifications of searches for systems in spectra of quasars. John would later considerably expand on this approach with his code Z-Search, which he further developed in the 90s for application to HST spectra. Along with his code to automate and objectify the identification process, John generated a set of rules to help eliminate the less likely candidates. As he said in his 1968 paper in which he first put forth these ideas, quote, "The above stated rules were designed to be sufficiently restrictive that identifications based on chance coincidence would not lead to accepted but unphysical redshifts. They are, in fact, sufficiently severe that they may exclude some physical redshifts. Our main purpose, however, was to try to make identifications in a way in which one could be confident that they were not accidental, instead of trying to identify every line." John was not afraid to get dirty with the data. but he knew how to avoid getting mired down in details that were distracting from the problem he was studying. After developing his new approach, he tested it on the excellent data available for Parkes 0237-23, and then would further demonstrate the utility of his approach on additional data sets as they became available. John did not think the best approach to a problem would always be simple. Jordi Miralda reminded me recently that John was very fond of quoting a note from John Wheeler that, quote, "Nature does not always choose the route that is easy to calculate." But John did like clear, well-posed problems, and liked to try and present his conclusions as clearly as possible. He recognized that if he effectively communicated not only his results, but his methods as well, others would be able to apply the same methods to expand on his work. To sum up John's first burst of quasar absorption line research, he set the course for the field in the late 1960s. He did this with a tremendous series of comprehensive papers, the product of tremendous work. In fact, I've decided John did not sleep from around 1965 to 1975. It's just not possible for him to have written so many papers, let alone do the work, if he had slept. And this doesn't even include all the work he was doing on solar neutrinos and other problems. I'm now going to cover two more examples of John's talent and success as a leader in quasar absorption line research, and they are related. His advocacy for the Large Space Telescope, Hubble, and his formulation, organization, and execution of the Quasar Absorption Line Survey, an HST key project. John recognized the great potential of a large space telescope to carry out superb science, and together with his friend Lyman Spitzer, was a strong proponent for the science HST would do, including its tremendous potential for quasar absorption line work. As I'm sure you will hear further this afternoon, as an observatory scientist for HST, John undertook a very broad and successful set of programs with Hubble. But I'm going to continue to focus on the absorption line work. So why was HST so valuable for absorption line research? As John pointed out in the 60s, the most likely absorption features you're going to find from the intervening gas occur in the rest frame ultraviolet. So in this color-coded chart where black is what you can observe from the ground, and this is the wavelength regime opened up by HST, you can see that the low redshift universe requires observing the UV. And this is where it's easiest to compare the absorbing material to other structures in the universe. In 1979, John had already spent more than a decade as an advocate of the Large Space Telescope, and he would continue this advocacy for the rest of his life. That year, in the middle of this gap of publications, when he prepared his contribution, Absorption Lines in the Spectra of Distant Objects, for the IAU meeting, Scientific Research with the Space Telescope, which was held here at the Institute, he still had another decade to wait for the launch of the observatory. In that paper, he outlined an ambitious set of observations addressing many problems, including the investigation of the distribution of absorbers at low redshift, how their properties evolved with cosmic time, how they relate to other constituents, the luminous baryonic matter, and he wanted to investigate what could then be learned from the absorbers about larger cosmological questions. This would require a very large program, a skilled team of experts, and a lot of hard work. John pulled together a strong team of leaders in the field, and they successfully competed and won the right to execute the Quasar Absorption Line survey. Ray Wyman recently shared the following with me, quote, "John's administrative skills contributed greatly to his, and those working with him, productivity. His organization of the key project was extremely well done and carefully thought through. In general, I was always struck by his ability to organize and define a problem and then explore it thoroughly." So with HST, we did a survey of approximately 80 lines of sight from redshift 0 to 1.6, and it provided, admittedly at only modest spectral resolution, the first census of quasar absorption line systems at low redshift. In this figure are the positions of the sight lines that we studied in galactic coordinates. This is a spectrum of a now very well-known high redshift quasar. The Lyman alpha forest is quite obvious. This is what the universe looks like at redshift of 3. And here's the spectrum of 3C273 that was obtained as part of the science verification program of the faint object spectrograph on the Hubble. The difference is obvious. This was the first quasar spectrum that John obtained with HST, and I remember we drove down to Baltimore to watch the data downlink, just for the fun of it. There was nothing we were going to do to affect the observations by being there. This was John's idea of showing a postdoc a good time. When the key project was completed, we were able to present this measure of the evolution in the number of observed absorption lines as a function of redshift. This was near the end of the 1990s. During the 90s, there had been two other major steps of progress in the study of quasar absorption line research. One was the commissioning of Keck with its high-resolution spectrograph that was providing exquisite high signal-to-noise, high-resolution data of the high redshift universe, like the spectrum I showed earlier. And theoretical models, particularly using ever more powerful simulations, were providing new insights into how the underlying distribution of dark matter, cosmology, and the ambient radiation field governed the appearance of the IGM. Significant portions of the theoretical progress was due to work by past members of the Institute, who, while not directly collaborating with John, were supported and mentored by him, and as you heard, sometimes told to go into this field. So I'm going to highlight results from people that all were here at one time or another and interacted with John, even though there are many other simulations I could compare to. In these panels, you see the evolution of the neutral gas from redshift 3 to 0, so 3 to 1.5, 1.5 to 0. And along any line of sight through this simulation, you can see that while the basic large-scale structure was in place very early on, there's a lot of change in the appearance of the absorbers. Dave and his collaborators were able to compare their simulations directly with our results. This is the kind of work John really appreciated, connecting careful theoretical work with real data. They used their comparison to conclude that at redshifts less than 1.6, the observed evolution was driven by both structure evolution and the decreasing amount of ambient ionizing radiation as the age of quasars declined, but that it was the evolution of this metagalactic UV radiation that dominated the observed changes in the properties of the Lyman alpha absorbers. Now, I mentioned that John also was very interested in trying to link or study the relationship between absorbers and other structures. And he was very excited when we first looked at this portion of the HST spectrum of 3C273, in particular because of the Lyman alpha absorbers that were at the same velocity as the Virgo cluster. Efforts were quickly made to compare the distribution of galaxies with absorbers, still a focus of ongoing research, with very mixed results. In particular, the lowest redshift 3C273 absorbers were not obviously associated with particular galaxies, but they were in the same velocity range and direction as the Virgo cluster. With hindsight, it is not too surprising that simple comparisons might not work. Even the high column density gas traced by its 21 centimeter emission can have a complex distribution relative to the easily observable starlight. While several groups continue to work on this problem, I'll use the liberty of being the speaker to show some of my own efforts, in part because they make use of the key project data and because they were inspired by my time working with John. Simon Morris, Ray Wyman, and I have used the CFHT to make a galaxy redshift survey towards 16 of the lines of sight we studied with Hubble in the key project. And so this is the combined line of sight to the quasars. These are the absorbers, and this is the impact, shows the impact perimeter to the galaxy. So you can do a comparison in the same volume of space of the distribution of galaxies and the absorbers. And what you find is that there's an overdensity at small velocity spacings. Sparing you the details, I'll just go to the conclusions, that we find a significant correlation between absorbers and galaxies out to scales as large as 1.5 megaparsecs. The correlation between the absorbers and galaxies is weaker than the correlation of galaxies with each other. The distribution of velocity differences for the carbon-4 absorbers and the galaxies is smaller than the corresponding distribution for Lyman alpha absorbers. This is consistent with absorbers spanning a range of conditions, including more pristine material that still traces the cosmic web of the baryons and more contaminated material enriched by the products of stars and galaxies. We're starting to compare our results to available simulations. Now, the simulations, which I'm trying to keep up with, move very rapidly, and I'm not going to try and pretend that I can summarize them, but they're starting to deal with providing physical insights wherever you might find gas on all scales. They're getting so sophisticated that they can even start looking at differences from a general simulation. What happens if you put a quasar in the foreground? How have things changed? So the problem is that with the additions of all these whistles and horns, we need to provide more constraints or end up with models burdened with extraneous details. So before the Space Telescope imaging spectrograph failed, this was the high-resolution successor to the faint object spectrograph and the GHRS. Some quasars were observed and provided exquisite data at high resolution, comparable to Keck's, and high signal to noise. This is the last spectrum that I obtained in collaboration with John, this time with me as the PI. The data are really spectacular, and if the cosmic origin spectrograph, a higher throughput spectrograph than STIS, gets added to Hubble sometime in the future, then it will be able to do a new quasar absorption line survey of 100 or more sight lines, but with a factor of 10 better spectral resolution. Like the first HST quasar absorption line survey, it will be following a path imagined by John Bahcall. Over the 15 years I knew John, he gave me great advice on a wide range of topics, but I'm most grateful for having had the chance to have fun doing science with him. If a leader is good, many will want to follow him. Great leaders find a way to get everyone where we all want to go, after having helped us recognize where that should be. John was a great scientific leader. Thank you.
Thank you for those beautiful remarks, Buell. I was so fascinated that I lost track of the time. But in fact, you didn't run over.
Good.
Do I understand you? I panicked just as you were showing what was a fascinating result. You're detecting a diminution in the heavy element content with distance from the nearest galaxy?
No. The velocity separation between the carbon-4 detected absorbers, and you have to remember that these things all have observational selection effects built into them, so that, in a sense, the higher column density systems with easily detected metals have a smaller velocity difference. Their distribution of velocity differences with all galaxies at all impact parameters is smaller than when you compare to Lyman alpha absorbers in general. So the picture is that, especially at higher column densities for the cognosante, say 10 to the 15th, 10 to the 16th and up, the material has been enriched above the low levels of carbon-4 that you're familiar with in the high Z forest.
Other questions? This is very rich science.
It's great science. It's fun.
Thank you, Buell. A long time ago, I wrote one paper on the distribution of stars around a massive black hole in the center of a galaxy for the purpose of seeing whether observations might give evidence that there really is a massive compact object. Some years after that, John got interested in the same problem. He said to me, John is a forthright person. He said, Jim, you were wise to keep that discussion to one paper. He was right. But it's a rich subject, too. And our Scott Tremaine from the Princeton University will speak on the present state of this rich subject.
Thank you. This subject is one that's marked by John Bahcall's footprints, and so I've tried to indicate that on the slides. The story starts with the recognition in the 1940s that a small percentage of galaxies contain a bright, unresolved central nucleus that, in its non-stellar radiation, has come to be called an active galactic nucleus. And it went into high gear with the discovery in the 1960s of quasars, which are by far the most luminous active galactic nuclei, with luminosities of 10 to the 13th solar luminosities, or 10 to 100 times the typical luminosity of a galaxy. This extremely high luminosity depends on the assumption that the redshifts of quasars are cosmological. And in the early 1970s, John was one of the most forceful and influential advocates of this view that quasars really were at very large distances, had very high luminosities, and that the redshifts were not due to either gravitation or some other funny effects. As part of that, he provided, along with Netta, the first evidence that some quasars were associated with clusters of galaxies at the same redshift. And perhaps more importantly, he engaged in a great debate with Chip Arp, which was published as a book called The Redshift Controversy, which I think convinced many scientists, including me, not only that the redshifts of quasars were cosmological, but also that in general, if there was a scientific argument, you were wise to take John's side. Now, the study of the luminosities of quasars has advanced exceptionally largely through two influential large-scale surveys, the 2DF survey and the Sloan Digital Sky survey. Here again, John's footprints are over the field because he was one of the early advocates of the Sloan survey, and the Institute for Advanced Study, through his efforts, was one of the first major partners of the Sloan survey. One of the reasons that it took so long to accept the fact that quasars were at cosmological distances is because in contrast to most other active galactic nuclei, the quasars are so bright that they hide the host galaxy at ground-based resolution. John recognized very early on that this was one of the arenas where the Hubble Telescope could make an enormous contribution. And in a very famous set of papers with Kurhakos and other collaborators, he took Hubble images of nearby galaxies, nearby quasars, and showed that in almost every case there was a well-defined galaxy of a variety of types hiding behind the quasar. The other remarkable feature of quasars is that their local co-moving number density evolves strongly. It's concentrated at redshifts 2 to 3. And this has now been shown most cleanly by a combination of the Sloan survey and the 2DF survey, which shows that the co-moving density at redshifts of around 2 is 1 to 2 orders of magnitude higher than it was either at redshifts of 5 or at the current epoch. Again, we see John's footprints because he was one of the first to conduct careful statistical studies of the redshift distribution and the cosmological evolution of quasars. We now recognize that the power source for active galactic nuclei is accretion onto a black hole of somewhere between 10 to the 6th and 10 to the 9 or 10 to the 10th solar masses. Here again we see John's footprints because in collaboration with Ed Salpeter, he wrote some of the first papers establishing crude constraints on quasar masses. The evidence that AGNs are the result of accretion onto a black hole comes from a wide variety of arenas, including very long-term stability of radio jets extending over megaparsecs, which requires that they're produced by an exceptionally stable gyroscope, such as a spinning black hole, by relativistic redshifted and relativistically broadened iron lines that models show are emitted from within a few times the Schwarzschild radius of a black hole, from relativistic or in fact superluminal motions in radio jets such as this one near M87, and also persuasively because the extraordinary energy output of quasars requires that they be produced with remarkable efficiency given the available fuel supplies. There's a natural measure of the efficiency of an AGN, the energy output divided by the rest mass energy of the fuel that's been input. For nuclear reactions, that's less than about 1%, but for accretion onto a black hole, for example, from a thin accretion disk, that efficiency can range from 6% up to 30, even 30 or 40% for a rotating black hole. And that extremely high efficiency is really the only way you can supply the quasars with a plausible amount of fuel. So if we believe that black holes are the power source for quasars, if the present co-moving number density of quasars is much less than the density at earlier epochs, and if quasars are found in the centers of galaxies, all of which statements are ones that John contributed to, then it must follow that many nearby galaxies have black holes at their centers, which are invisible because, most likely because they're now starved for fuel. That remarkable prediction, which dates back to the early 1970s, has now been confirmed in a wide variety of cases. The most obvious is the center of our own Milky Way galaxy, where infrared observations show the presence of stars orbiting on Kepler orbits around the presumed center of the galaxy at the radio source Sagittarius A star. This has an orbital period of about 16 years and has now been followed most of the way through a period. There are half a dozen other stars whose orbits are gradually being refined. The remarkable thing about this is that because this orbit is a closed ellipse, that tells you that the potential is Keplerian down to the pericenter distance of the orbit, which is only about 100 astronomical units. Combining the period with the size of the orbit and Kepler's law, you can estimate a mass of a little over between 3 and 4 million solar masses. That requires that that mass of millions of solar masses is concentrated into a size which is less than a couple of times the distance of the outer planets in the solar system. And the only plausible astrophysical object, even the only implausible astrophysical object we know of that could be so compact is a black hole. The second Gould case is the galaxy NGC 4258, which has a disk containing masers. The velocities of the masers exhibit a near perfect Keplerian rotation curve out here, which gives you an estimate. Again, says there must be a compact central mass and gives you a mass estimate. Moreover, the masers that are in front of the source at the center of the galaxy have a proper motion across the sky, which gives you a second measurement of the mass, and also exhibit an acceleration, a drift velocity of 9 kilometers per second per year. That's simply the centripetal acceleration of the objects in the disk going around the central mass. That gives us 3 independent estimates of the mass, which can be combined to provide an estimate of the mass and an estimate of the distance, or 2 estimates of the distance that are accurate to within about 2%. These are the most accurate distances we have for any galaxy, any other galaxy outside our own, and have been used as an anchor for the entire extragalactic distance scale. Well, those are the 2 best cases of black holes in galaxies. To do anything further, you have to go to the Hubble Telescope, and here John's footprints are enormous, not just because of the central role he played in development of the telescope itself, but also because of the role that he played in making the telescope a really efficient instrument for doing first-rate science research. The nearest case is the black hole in M31. This is the nearest large galaxy to our own with a sequence. This is a sequence of images at greater and greater resolution, which end up with a Hubble Telescope image that basically show 3 sources. The red sources, P1 and P2, appear double, but in fact are almost certainly an eccentric disk of stars orbiting a black hole at the location of this small blue source, P3, fitting the kinematics of the stars around in this disk. Give you an estimate for the mass of the black hole of 10 to the 8th solar masses. The characteristic signatures that you see are a rapid rise in the velocity dispersion near the center, going up to almost 400 kilometers per second. The 2 curves are ground-based and Hubble data, and the evidence is far more convincing in the Hubble data. And a sharply rising rotation curve that's also much clearer in the Hubble data than in the ground-based data. But you can do more. Because of the difference in colors associated with the spectrum of P3, you can isolate the stars that are in this small blue source. They give they're clearly A stars. This is a spectrum that shows the Balmer series The reason it looks different from the Balmer series from an ordinary star is that the lines have been broadened by the Doppler motions of the stars. The resulting velocity dispersion is almost 1,000 kilometers per second, a factor of 2 higher than you see in any other galaxy, and that's because these stars has to be because the stars are so close to a central black hole. The mass that you get for that black hole by modeling of the stars in that small blue disk comes out to be slightly over 10 to the 8th solar masses, completely consistent with the estimate that we already had from the stars at larger radii. It provides an upper limit to the size of the central body, less than 1/10 of a parsec. Because that's so small, it once again means that the only astrophysical system that can explain the data is a black hole. Beyond M31, you have to use more statistical techniques. Basically, you know that the black hole is going to be at the center of the galaxy, so you use Hubble to do photometry of the stars around the center, and you use Hubble to measure the velocity distribution of the stars close to the center and look for a rise in the dispersion or the rotation curve near the center, and then fit to models of the stellar distribution. Here again, John had an influence because many of the aspects, the dynamical interactions of nuclear black holes with the surrounding system were first worked out by Bahcall and Wolf in the context of globular clusters. We don't yet have secure evidence for black holes in the centers of globular clusters, but it may well be that in the next decade, the context John was originally interested in will prove to be important. That's an example of the data that you can get with Hubble showing the rise in dispersion and the rise in rotation curve near the center. That's an example of one of the tests you can do using the code from our group called the Nuker group, comparing the chi-squared as a function of black hole mass and comparing that with data from the Leiden group led by Tim DeZeu, and combining the various data and the various codes, you always get a consistent answer for a black hole mass of about 40 million solar masses. You can also do a test by looking at the galaxy NGC 4258. Once again, you have a maser mass for that of 3.8 times 10 to the 7th. The best fit stellar dynamical mass is within 20% of that and within more or less within the error bars. So I think the results are quite convincing. We now have something like 30 reliable galaxies with reliable black hole masses. The black hole mass is roughly proportional to the luminosity of the host galaxy, but a better correlation is with the velocity dispersion of the host galaxy. So once you know this, that this correlation is present, you can start to look at the demographics of the black holes. And that can be specified by 2 numbers. One is what's called the Cormandy number, which is an estimate of the local density of black holes in the nuclei of galaxies, which is derived from that mass dispersion or mass luminosity relation and our knowledge of the luminosity function and the density of galaxies. That gives you somewhere between 2 and 6 times 10 to the 5th solar masses per cubic parsec. The second is the Sultan number, which is derived in a completely different way. You take the total luminosity of all the quasars that you see, add up that luminosity, assume some efficiency for the conversion of mass into photons, add that up, and you come out with a number that within the error bars is exactly the same. That really remarkable agreement tells you that the efficiency of the radiative efficiency of quasars is around 10%. Once again, the only way to get that efficiency is from black holes. It tells you that quasars grow in their luminous phases, not in their dark phases. It tells you that we've identified most of the AGNs and most of the AGN luminosity, and that the black holes that are found in quasars are mostly in the centers of galaxies. So to summarize, I think in the 40 years since quasars were discovered, there's been really spectacular convergence of our understanding of the most dramatic observational objects in astrophysics, that is quasars, and the most dramatic constructs in theoretical physics, that is black holes. We now have strong evidence for massive black holes in 20 to 30 nearby galaxies in the range of millions to billions of solar masses. For at least 3 of them, we know for sure they have to be black holes, and almost certainly all of them are. Every galaxy with a massive spheroidal component appears to have a nuclear black hole, and the local black hole mass density and demographics is consistent with what you'd expect if the efficiency of quasars is around 10%. This remarkable advance in our understanding between 1970 and the present almost exactly corresponds with the period of John's career. And although not all these advances are directly due to John, I think the fact of that the fact of that agreement is certainly no coincidence.
Scott, thank you. Discussion. I think, Ed Turner, you were the one who emphasized how striking it is that the quasar number density rises so rapidly with increasing time to a redshift of about 1.5 and then plummets.
Yes, it's very, we saw the universe with eyes that only saw quasar light. It basically flashes off for about a tenth of the lifetime of the whole universe. It shuts off very, very rapidly. So from these conclusions, we have to assume that almost all the mass that's currently in black holes was accreted in that little narrow ring of time.
What do you say?
I'm confident that the people who make models of galaxy formation can explain it. And we just had a talk earlier this week.
Binaries, there's lots of talk about galaxies forming by merging. Is there lots of talk about binary black holes?
There's lots of talk about it, and binary black holes are extremely important to a lot of people because they would like to see gravitational radiation from the merger of the binary black holes. The issue is whether the binaries hang up and survive for a Hubble time,
Right.
or whether they do actually merge. But everyone would certainly like them to merge.
If they don't merge, they're there as binaries and detectable?
The binaries are very hard to detect, and there's rather little direct evidence for binary black holes except in 1 or 2 cases. But again, the hope is that the LISA spacecraft in the next decade will see the gravitational radiation from the in-spiral.
That will be very exciting. Let us thank Scott again. I'm now shifting roles to Meta Chair for the purpose of introducing the chair, who is Ray Siniera. Ray, your roots at Princeton go very deep. You worked with me, it must have seemed like an eternity, on the space distribution of galaxies, the statistical pattern, and the realization of models that show us that we have about the right pattern. I still use those models in public lectures. You then moved to the Institute.
Essentially because of your relationship with John, and there was a real synergy there.
And you worked with John on the structure of the galaxy, with Netta on the structures of clusters of galaxies and clusters of clusters.
And I think with Safi, as a matter of fact, a little bit he was writing articles. He was in middle school, I think, writing articles for Byte magazine. And we had some, we never collaborated, we never wrote something, but we talked about computers, et cetera, back then. So I think I've collaborated with 3 Bahcalls.
And you have taken your expertise in handling data, in handling images, and in handling concepts to your own firm. It is called DisplayMate Co.
DisplayMate Technologies.
DisplayMate Technology. Ray?
Thank you, Jim. Before I introduce Andy Gould's talk on the Bahcall-Siniera galaxy model, I thought I'd take a few moments just to talk about how it came to be. It was kind of a serendipitous, unexpected result, kind of a footnote turned into a headline, and it really shows, how John's nose or eye for a good problem and how to get, some spectacular results when the circumstances present you with an opportunity. as Jim mentioned, I'd worked with him on galaxy clustering models, which are essentially little mini model universes. And John's idea, and he invited me to the Institute for this, was to build model universes, and we would then make predictions of what the Space Telescope would see, essentially looking at variations in all of the known parameters, so that when the Space Telescope turned on, we'd know, either we'd learn something about the parameters or learn what we unexpected results and know what was new and what was different. And so this was going to lead into a series of papers called The Universe at Faint Magnitudes, and it was primarily a cosmology study, and we were just going to build these deep models. And but there was a concern that at 28th magnitude with the Space Telescope, the stars in the Milky Way might get in the way. It was really not known how many there were going to be, and could they mess things up? Would they interfere with the cosmology? So, and neither John or I were galactic astronomers, and really both our backgrounds on in cosmology. In fact, mine was entirely in cosmology. So we built a very simple model. The idea was really just to get a handle on the stars, and so we built a very simple model. We spliced together the information from external galaxies and attached that to whatever local data we could find, and we built a very simple model of the galaxy, just a bunch of equations and some normalization constants. And what was amazing is how accurately they predicted all of the available data for the star counts. And John, with his extensive personal connections and professional connections, got us lots of new data. So we spent actually 5 years exploring and exploiting this model. We had lots of fun with all of the people that traveled through the Institute. Jan Orff, for example, was a frequent visitor in the late 70s and early 80s, and Jan was amazed at what we'd done. He said he'd never been able to do anything like that because he was so close to the data, but we didn't have that problem. But it worked so well, and we looked at so many things from this three-dimensional model here. We looked at the spheroid stars. We looked at massive halo stars. We looked at QSOs because they were masquerading, essentially could masquerade in the star counts as stars. We looked at wide binaries, so I got to play correlation function games with stars. And one amazing benefit, actually, that really helped the Space Telescope is that we discovered that there weren't going to be as many guide stars as had been assumed in the design of the Space Telescope. So then we worked on a paper that essentially allowed, I guess, perhaps the engineers at the Space Telescope, but also some new strategies on how the Space Telescope could lock onto guide stars. I no longer work in astrophysics, so I'm actually very curious to find out what Andy Gould is going to say about the Bahcall-Sanira model since I left in 1983.
Set correctly for this, isn't it? I don't know what it's set up. Is this on? Okay, so I'm going to try to review John's work on galaxy models. I'll try to touch on the Oort limit and his work in wide binaries as a probe of dark matter, but I'll really only be able to talk very briefly about that. John's work in this area is characterized by three different, real periods. One is from 79 to really 78, when he began work on this, to 85, when there was just an explosion of new results and ideas, which I'll try to briefly review. For the next decade, he was quite interested in this area and had a guiding hand in additional research, although he didn't have the same level of intensity of work in it. And then in the most recent decade, he had continuing interest, but really was kind of hands-off. And most of what came out of this is sort of the natural outcome of his previous work rather than his direct intervention. So this is the idea of the Bahcall-Ciñeira model. So if Bahcall and Ciñeira had lived in the Sombrero Galaxy, they would be looking off in these different directions and doing star counts. Now, this is not an original idea with John. I think this goes back to William Herschel. But what differentiates Bahcall-Ciñeira from previous work in this area is that they took the attitude of having a forward model. So previously, people had tried to invert star counts and construct a model of the galaxy from that. And instead, they took the attitude that you could look at external galaxies and figured out basically what it looked like, and then try to model our galaxy, with that information. So the inputs to this were basic shapes that came out of this external galaxies, just that they're composed of exponential disks and spheroids, which had a couple of different shapes that they tried, but wound up with de Vaucouleurs profiles. And then some information from our galaxy, very local studies of luminosity functions, color magnitude relations, etc. And of course, star counts. Now the star counts, Ray didn't mention, but he had to go back and look through dusty old volumes in the Institute Library from 1925 from Stearns, I think, when they looked at special areas that were originally identified by Kapteyn, as well as some more recent star count data. And so from these, they were able to reconstruct, identify, measure all the parameters of this model, and then try to figure out if there were additional structures not found in the models. So, as I said, there were a huge number of results. Ray mentioned there were limits on quasars. There's one very striking result is just they came up with their models based on what external galaxies look like, which is all bright stars. But in our galaxy, they were trying to measure parameters, and it was all based on dim stars. And so it just shows that those trace the same structure, which is something you would expect, but it's interesting that you could prove it. And a big interest of John's was trying to figure out if stars made up the dark halo. So the composition of the dark matter is still unknown, but at that time it was believed that it might well be made of stars, and so this was a major area. I'm not going to be able to review in detail all of the different contributions, but I did want to focus on one issue just to show how the model works and how it leads to quantitative results. So this is this long-standing controversy, which goes on today, as to whether there's a third component in addition to the disk and spheroid needed to explain star counts. And this is a classic, Bahcall-Ciñeira papers are filled with dozens of diagrams like this. But this one serves to illustrate that there are basically two components. So if we look up toward the North Galactic Pole at 20th magnitude, then we see a bunch of red stars. And that's because we're seeing the disk, which is not too far away. So the stars in it are fairly dim if we can see them at 20th magnitude. And so they're dim, and so they're lower main sequence stars, M stars, so they're red. And on the other hand, the spheroid stars are 6 or 8 times farther away, so they're a few magnitudes brighter to be able to see them, and hence they're much bluer. So you see these two spikes indicate two components. And as far back as 1965, I think, people had been positing that there was a third component needed. I'm not sure exactly why, but anyway, Bahcall and Ciñeira said, well, no, there's no third component here. There's just these two components. Of course, they said, well, there could be a third component. And that was the great beauty of this model. Instead of being sort of vague, they could say quantitatively, if we put in a third component that has a scale height of a kiloparsec, how much density can it have relative to the disk and still be buried under this diagram? So the answer to that was that it had to be, I don't know, at least 10 times less dense than the disk. And when people have put forward third components since then, it's been in conformity with that limit. Nevertheless, there's an ongoing debate, and John was really part of this debate, trying to figure out if there is a third component. So with Casertano and Ratnatunga, he showed a few years after this that in order to explain local kinematic data, you really couldn't do it based on 2 Gaussians. You'd need 3 Gaussians. But there's one characteristic of John. He was very, he didn't lightly go from some new result to, implying a fundamental conclusion from that. It's well known that if you have a distribution with a large kurtosis, that it's going to take, it can't be explained by 1 Gaussian, and the fit's going to be better with 2 Gaussians. But from this fact, from the fact that the disk had to be broken up into 2 Gaussians, he did not therefore conclude that there was really a separate structure. He just thought it could have been an extended structure. Whereas other people, I think, immediately leapt to the idea that there was a thick disk. And so this controversy has continued for several decades, and I'd say it's really not resolved to this point, although I think most people characterize these hotter population of stars as a thick disk. The independent nature of the thick disk really rests on still somewhat tenuous evidence, although it's becoming more believable. Well, in addition to being able to get immediate results, John was also looking to the future. And as Ray mentioned, these papers also have a huge number of diagrams saying what's going to be happening at 28th magnitude, which is very striking because at the time it was 1,000 times fainter than people were able to do at that time, probing these issues of a dark halo and the disk luminosity function. They also came up with ideas for doing star counts in various different directions in order to pin down galactic parameters. So this model has a huge number of applications. Just to mention 1 or 2 of them, in telescope design, people are using this still today to try to figure out whether their guide star cameras can find enough guide stars. And as Ray mentioned, that was one of the first applications of the model. So I just looked up there, 736 citations, 27 of them in the last 10 months, which indicates that the rate of citations is essentially constant over 25 years. And they have also made this model publicly available, so people can check it out themselves or modify it and see what it produces. So John was very interested in getting Hubble images of this faint star population. At the beginning, it was kind of disappointing. We had this aberrated mirror, and actually we had to deal with very short exposures, and you can see trailed images because the exposures were so short that we dispensed with guide stars. But anyway, some things were found then. But really, it wasn't until the mirror was repaired that the telescope had the potential that John originally envisaged for dealing with this problem. And we looked at this field and tried to see if there were, in fact, a lot of M dwarfs in it, and there weren't. I mean, we looked at a blank field, or anyway, we took somebody else's blank field, and we analyzed it and found that there were hardly any M dwarfs. And so that ruled out this idea that the dark halo was composed of these very faint stars. And the Hubble Publicity Office became very excited about this and wanted to do a press release of it. And they have lots of beautiful press releases of all kinds of stuff that they're used to putting out. And I was very curious to see how they would handle doing a press release about a blank field. And so they said, well, here's the blank field, but here's what it would look like if it had a lot of M stars in it. So after that, John and Chris Flynn and I, Chris did most of the work of poking through all these fields to try to find all these stars. So we found over 1,000 stars. And then, we appended some collaborators, including Zheng, who's here now. And we found a huge number of M dwarfs and were really able to map out the faint end of the luminosity function. So this is what our luminosity function looks like. But the important point I want to raise here is that this bold histogram shows the distribution of heights above the plane. So these stars are not only dim, but they're very far away. So they're very, very faint, which is why we needed Hubble to see them. And they're really thick disk stars. So it took a while for John to sign off on thick disk being in the paper. So Chris Flynn, convinced him of this, that by this time maybe the thick disk was really how you had to deal with these stars. But very recently, a French group, Jannuzi group, for some time, there was a very sharp conflict between this luminosity function and the luminosity function determined from local stars, which kind of heads out more flat here. I didn't show it. And I always thought that this was due to poor statistics of the nearby sample, which just came from within 8 parsecs. But the Jannuzi group has shown that through ground-based star counts that difference persists. And so it's likely that the thick disk luminosity function and the disk luminosity function actually differ at faint magnitudes. So that's a pretty exciting result, which has taken, I don't know, 15 years to come out. Well, we also looked at spheroid stars. So here, to find spheroid stars without any kinematic data, we just took the stars that were so faint that they couldn't possibly be disk stars and analyzed them. And you can see we could get out to 50 kiloparsecs looking at the spheroid. And here again, there's very interesting differences in the luminosity function. So this GFB is the luminosity function derived from this Hubble counts very far away. And you see that it agrees very well with these local samples, one of which I did and one of which was done by Conrad Don and collaborators. They agree down here at the bright end, but at the faint end, there's many more stars. And so it's not known whether the nearby spheroid and the distant spheroid really are that different. This is the only piece of evidence in that direction, but it's something that, again, is at the forefront of this subject. So I don't know, how much time do I have left? 5. Okay, so I think that so John worked in two areas that were closely related to this that I want to at least say something about. One is the Oort limit, or the problem of disk dark matter. Well, as you can tell from the name Oort limit, John was not the first one to work in this, but Jan Oort had concluded that half of the matter in the disk was not accounted for by stars, or stars and gas. So for all the stars that there were, there's, again, as much other matter and something else. And so I first noticed John remarking on this in the Bahcall papers, and then he became interested in really tracking it down. And I think his major contribution here was to develop a self-consistent method of assessing this problem. So what he did was, he first of all collected data on what were all the different populations of stars, and each one had a local density and a velocity dispersion. And then what he did was, so this is at the plane of the galaxy, and then he just began populating the space above the plane using the Poisson and Boltzmann equations together, and populated with all these stars, and then he would measure the potential from those stars and ask whether that potential was consistent with the data from tracers that were sitting in the potential, K giants or F dwarfs. And so he concluded, like Oort had, but on a much more mathematically sophisticated basis, that there was a fair amount of disk dark matter. Well, it turns out there isn't really any disk dark matter. So other people using much better data sets and variants of the method pioneered by John have shown that really perhaps there's 10% disk dark matter or less. It's really very tightly constrained, especially with Hipparcos data. So the key thing was to develop the method, but the data, I guess you would say that the spirit was willing, but the data were weak at this time. But that got John interested in another problem of actually trying to figure out what this disk dark matter was. And he developed the first method with Pete Hutt and Scott Tremaine to try to probe this disk dark matter. So the idea was that he noticed, actually also from work with Ray Siniera, he'd been collecting data on binaries, and some of these binaries were quite wide. They were separated by 1/10 of a parsec. And so John reasoned that these wide binaries could not survive in the face of perturbations from, massive objects in the disk. So John and Pete worked on, modeling this with, simulations, how rapidly these binaries, or these 1/10 of a parsec binaries, would get ripped apart depending on what the disk dark matter was made of. So if it was made of very massive stuff, then they would all get knocked apart in a few 100 million years. And then less massive, they'd be knocked apart in a couple of billion years. And so they put these limits of 2 solar masses for the mass of the disk dark matter. Well, again, John was way ahead of what was actually doable with the data. So it had very small samples, and Martin Weinberg showed that with these small samples there were other effects that came in, and you couldn't really conclude much definite on the basis of that. However, the same method, now that we have much better data, and so there's much larger samples of binaries instead of the 3 or 4 binaries that John was dealing with in this regime. We have dozens of binaries, and so recently it has in fact been possible to place limits on dark matter, not this dark matter, which doesn't really exist, but halo dark matter, using this technique. So again, John was about 20 years ahead of his time in terms of seeing that there's this path forward, but then having to wait decades for the appropriate data. So I don't think I'll go through these conclusions. I think they're evident. I mean, the major point I want to make is that in addition to developing all these rigorous methods, the test of time is that this is having continuing impact, and there's still ongoing work, on the basis that John had originally laid out. Thanks.
I have a question, Andy. Have there been studies on the star counts, which is the raw data from the model to 28th magnitude? Have people looked at that, or have they been looking at the kind of specialized particulars of?
I think people have really attempted to model the data that they had rather than, so the Hubble data go to about 26th or 27th magnitude, and we have, tried to match those, yeah.
Okay. Are there any other questions?
How much is the interpretation of the star counts now exhibit total, particularly trying to get galactic parameters affected by fluctuations and screens and so forth in the outer world? What is that?
Well, it's not affected in our thinking at all, but whether it should be affected, I guess I'd have to defer on that because I haven't thought about it very clearly. I think what basically we're looking, the sampling that we did with Hubble is over so many dispersed fields rather than individual fields that I think it's unlikely to. So there's sort of 2 or 3 stars in a field. So I think on those grounds you're getting an average and not affected by fluctuations.
Any other questions? Yeah.
Is it now known what the dark matter is?
No. So it's known not to be stars. Of course, it's known not to be stars from not appearing in star counts. It's also known not to be lumpy things at all from microlensing. Or at least it can't be more than 20% of the dark matter. So the best guess is WIMPs, but really there's no firm evidence for it. It's the lack of evidence for other things that brings the WIMPs to their high standing.
Other questions? Andy, thank you very much for a great talk.
Are you going to undo this?
Yes.
Okay.
I shall again assume role of meta chair for the purpose of introducing the chair, Sarah Seeger, Department of Terrestrial Magnetism, an anachronistic name of the Carnegie Institutions of Washington. While she was a member of the Institute, she wrote a paper with Wayne Hu and me that must be characterized as questioning authority in cosmology, in particular the evidence for a cosmological constant. On reflection, I'm sorry very much that I didn't ask John his opinion of whether we should write this paper, because he was so very protective of the people in his group. But I think he would have agreed this is a case where you really ought to question authority. He would have agreed also that these 2 young people have enough authority on their own that it worked out just fine. She is an authority on recombination in the early universe and an authority on planets outside the solar system. Sarah Seeger.
I have a brief story related to the next talk, but first I wanted to start out by saying that although my scientific work did not overlap with John, I nevertheless benefited tremendously from interacting with him when I was a member here. John was not only an excellent mentor to me, but he was like a father to me, and I regard him now as my scientific father. I was really fortunate to be here at the time of the resolution of the solar neutrino problem and the Sudbury Neutrino Observatory results, because it was truly inspiring and amazing to see this conclusion of the solar neutrino problem and John's hard work. In that summer, I was also working very hard for another reason, and I always saw him no matter what time I was there, 6 in the morning, midnight, he was always working hard. We members love to speculate about John and his actions and decisions and what was behind those. And in particular, I wondered what drove him to stick with the solar model problem for so many years. And specifically, I asked him, when was he confident that his solar models were right and that new physics was the answer to the solar neutrino problem? And he answered with one word: helioseismology. That's the subject of the next talk. Now, the flip side of the stunning conclusion to the solar neutrino problem for the members here was that John was away a lot more than usual. And for some of the new members, this was a bit of a problem because they wanted to have more faculty around and more interaction. And that's when Peter started showing up. And he became faculty here and now is around and interacts a lot with the members. So Peter, as everybody knows, he retired from Caltech and now he's a faculty here, and he's going to tell us about helioseismology. Peter.
Okay, well, it's natural that somebody who was interested in neutrinos from the sun would also be interested in helioseismology, because while the neutrino story started as a way of understanding the interior of the sun and later turned out to be a way of understanding something about neutrinos, helioseismology was another way of seeing what was going on inside the sun. So I'm going to try to give you a very brief overview of both the history and the content of helioseismology. So this is a cutaway cartoon of the sun, and the important parts here for us going out from the middle are the core where nuclear fusion occurs, a radiative layer in which energy is transported by photon diffusion. So the core is the white part, the radiative zone is the yellowish part, and then the orange part is the convection zone, which we know partly from helioseismology is about the outer 30% of the sun by radius, in which energy is transported by fluid motion. And at the top of the convection zone, where the density of the gas is very low, the convective motions become close to sonic, few tenths of sonic. And these vigorous convection motions, turbulence, the convective turbulence, emits acoustic waves, and these acoustic waves in some frequencies resonate with inside the solar cavity, and this is why we have helioseismology. So unlike the Earth, which only shakes measurably after big earthquakes, the sun is shaking all the time, and in about 10 million measurable detectable modes. So this subject started in the early 1960s with work by Leighton, Noyes, and Simon, who detected oscillations with periods of around 5 minutes at discrete, localized positions on the surface of the sun. It was another several years until in '69, Roger Ulrich, a former collaborator of John's, understood that these were the incoherent superposition of many normal modes of the sun. And then the next really big breakthrough was in '77, when Franz Deubner was able to actually locate or determine the dispersion curve, a rough dispersion curve, for these modes observationally. And I'll show you some more recent data. So I have only 5 slides. What is this? Okay, so this shows a Dopplergram. On the left, this is a modern Dopplergram. This is taken from a spacecraft, a SOHO spacecraft, from an interferometer, and it's what's being measured here is the radial velocity of many different points on the surface of the sun, just a line of sight Doppler velocity. And you can see the scale here goes in meters per second from minus 2,500 to plus 2,000. So this is a couple of kilometers per second, plus and minus. And the biggest effect you can see is the red on the left and the yellow on the right, and this is the solar rotation. But you can subtract out the solar rotation by taking an average of many of these images and then just subtracting it from an individual image, and then you get a Dopplergram that's on the right, in which the solar rotation no longer appears. Now the scale goes from half a kilometer a second negative to half a kilometer per second positive in different spots with small scales. And this is the basic data set that's used to drag out the modal amplitudes and frequencies. So what's done is one of these is taken about every minute, and then the velocities are projected on spherical harmonics. So you just imagine for each spherical harmonic, each minute you get a number, and then you have a time series of these amplitudes for each spherical harmonic, and you make a temporal power spectrum from these time series, and you get what's called a K-omega diagram, and that's shown here. So these ridges that you're seeing on this K-omega diagram, the K is the angular degree of the spherical harmonic, and the omega is the frequency of these peaks in the spectrum. The power lines up along these ridges, along all these different ridges. And these ridges, starting with the faintest lower one and going up vertically, correspond to sequences of modes with different numbers of radial nodes in the sun. So the lowest one, which you can barely see here, is what we call an F mode. It has 0 radial nodes in the sun. The amplitude of oscillation just decays exponentially inward. And then we have 1, 2, 3, 4, 5, and so on. And the biggest concentration of power is with periods of around 5 minutes, frequency of around 3 in these units. These are millihertz, 3 millihertz. So this is the basic data. If the data was displayed in a different way, you'd actually see that the modes are discrete points along here. And this is sort of low to middle degree in angle modes. The modes actually go out to a couple of thousand in angular degree. So this is the data. Individual modes have surface velocity amplitudes that are maximum, for the most highly excited modes, maximal about 20 centimeters per second at the surface of the sun, but modes can be detected with surface velocities as small as a millimeter per second on the surface of the sun. It's an advantage of having lots of photons. The energies of individual modes are of the order of 10 to the 27 ergs, and with 10 million of them, if you add that all up, the total energy in oscillation in the sun corresponds to a couple of seconds of solar output. And the modes have lifetimes in the most highly excited band of days, and at the lowest frequencies that can be observed of maybe, well, at least more than several months. So this is the sort of data. The energies of the modes are basically determined by equipetition between the energy of convective eddies, single convective eddies in the surface layers of the sun, and the energies of the modes. And that's where the 10 to the 27 ergs comes from. Okay, so that's more or less history and current state of data. These modes that have been detected are basically trapped acoustic waves. They're sound waves which reflect below the temperature minimum in the solar atmosphere back into the sun. And There is another set of modes that the sun possesses, which are called gravity modes. These have never been detected. Predictions for their amplitudes are slightly below what can be detected at present. Someday maybe we'll detect these gravity modes. The gravity modes are interesting because they're complementary to the acoustic modes. The acoustic modes mainly tell us what the sound speed run is with depth in the sun. The gravity modes would tell us what the stratification, stable stratification or lack of it, is as a function of depth in the sun. And the acoustic modes mostly tell us about the outer part of the sun. The gravity modes, if we could detect them, would tell us about the inner parts. Okay. Yeah. So now I want to just show you two slides based on recent work that John was connected. Oh, gosh. I'm not up to this. Oh, yeah, we got rid of it anyway. Okay. So this is one contribution that John made, was involved in making to the helioseismology per se. And that was, of course, he always was fitting his models to the helioseismic data. And you can see here, in this paper, which was from 1997, well, submitted in 1996, you can see about how well the standard models that he was building with Pinsonneau, Basu, and Christensen-Dalsgaard fit the observed or the observationally determined run of sound speeds. So what you see here is the difference between the model and the observationally determined sound speeds divided, normalized by the observationally determined sound speeds for standard models. And you see in the dashed line about how good this fit was. It was somewhat better than the 1% level throughout the sun. And then you see what happens if you add the effects of elemental diffusion, which are really quite small, most important right near the base of the convection zone, in improving this fit. So you see now the fit is good at about 0.2% level. So this is one contribution that he made. And now I'm going to show you the most recent work from last year, or this year, I guess, on trying to understand how recent reanalysis of photospheric absorption line data, which changed the estimates, determinations of the heavy element abundance. By heavy element abundance, I mean everything heavier than helium. In the surface layers of the sun, the photospheres of the sun, affected these fits. So this is the sort of latest word in this subject. The reanalysis of this photospheric data, absorption line data, gave abundances for CNO, silicon, about 30% lower, maybe 35% lower than previously used to get this beautiful agreement. It also brought these abundances in better agreement with data from hot stars and also from the interstellar medium. But now, if you look at what happened to these fits, you see for the sound speed, these beautiful fits as shown by the blue curve have now gotten much worse. And similarly, the fits for the density, which are not nearly as good, because density isn't the primary thing you get from acoustic waves, have also gotten much worse. So what looked like a great fit between model and data now doesn't look so good. So you have to ask yourself, was it an accident that the fits were so good? Did people just work until the models fit the data? Or maybe the reanalysis, the improved analysis of the photospheric abundances is incorrect. And we don't know the answer. He didn't know the answer. He was very much involved in working on this at the end of his life. Okay, that's all I have to say about science. I now have I want to just say two things. One personal thing. I met John in 1964. He was quite a character even then. By the end of the year, Caltech had offered me a job. I was already working at the University of California, and I didn't go. And then John and I decided we'd like to work in the same place, so we sort of shopped around for places that would be willing to hire both of us. But for some reason or other, Caltech was the only one that was willing. And so the year after, I went to Caltech, and I was there for 36 years. And then I decided I had enough. And John got Natty Seiberg to call me up and tell me I should come to the Institute. Well, Natty said he thought of it, but everybody knows that John put him up to this. So I've had a long history with John, and he really was a remarkable person.